And as I rotate this wheel, I get a 14-bit digital value of the precise angle to 0.0219 degrees precision using an SPI interface and no microcontroller. Let me show you how I built this. In a previous video, I built this interface for an I2C using the AS5600, which gives you a 12-bit digital value of a magnetic rotary encoding, and it required a lot of parts in order to make it happen. This entire board with all these chips just to make this happen without a microcontroller. And you can see the way that works. You have to send a start condition, precise clocking of the address of the device, let it acknowledge, and then you have to send the command to the device to tell it to read from the angle sensor, and then you have to clock in the device again, the device address again, and at the end you press the button and you finally get data out, and it's 12-bit data. So this was a little bit painful to do without a microcontroller. So I got my hands on this AS5047P magnetic rotary encoder that uses serial peripheral interface. And it comes in this breakout board like this one from SideView Tech, which I ordered on Amazon. And it has the classic pins, which include MOSI, which is master out, slave in, master in, slave out, MISO, the serial clock, and the chip select pin. And those are the only real 4 pins that you need. It comes with little headers that you could solder on, and a magnet as well. And you could use it as 3.3 volts mode or 5.5 volts. In order to do the 5.5 volts, you have to sever a little connection in the back where you could see it's clearly labeled on the breakout board. Let me zoom in on it. And all you have to do is take an X-Acto knife and just cut this, or a razor blade, and cut this and use a multimeter to make sure there's no continuity. So let's talk about the serial peripheral interface. This is a mode 1 SPI device, which means that the clock polarity is 0 and the clock phase is 1. What does that mean? The clock polarity means that the serial clock is normally in the low position and goes high, and in order to clock data, and the data is clocked, that's the CPHA, is clocked on the falling edge of the peripheral clock. And so the way this chip works is that you have to send it commands on the MOSI line, and you have to receive data on the MISO line. So basically, first you have to drive the chip select line low, and then you clock in 16 bits of 16 clock cycles. And then in order to reset the peripheral interface, the angle sensor, you have to drive the chip select line high again and then low again in order to start the next cycle. The interesting thing is that the command that you have to send to the device is on the MOSI line is the command to read the angle sensor. And you have to include a parity bit, which when you include the read angle sensor is always 1. Because of this, you could just tie the MOSI line, or the serial data input line, to 5 volts and just leave it there, and you're constantly sending the same data to read the angle sensor. So now I wired the board up with the MOSI line to VCC, and basically put wires on all the other pin headers. And we're going to test this out by bit banging this manually with the button. I have this big video game button here, so let's see how this works. This is SPI, considerably easier. That's it. So the first step in making an interface for this is making a serial clock. So I'm going to make a fast clock using a CD4106. So the clock for this is very easy. Basically, we're using a CD4106 inverting Schmidt trigger and powered with 5 volts and ground, and it has 6 of these inverting Schmidt triggers on them, and I have a 47 nanofarad capacitor to ground at the input and a 2.2K resistor here. And so that is the clock. So that clock signal is coming out, and you can see it here. Let me get rid of the channel here, the other channel here, and that's a very fast clock. It's 6.5 kilohertz. You can make it faster, but it's going to serve the needs, and it gives you a relatively stable clock signal. Next, we take that clock and we put it through a set of 2 CD4017 decade counter chips and count to 16, because that's how many clock ticks we need per data cycle. So that clock signal that we just made is going into CD4017 counter, 2 of them actually, and it's basically counting to 16. And so the red wire from the second chip, well, these are cascaded, so it's counting, it counts to 2 digits, and these are 2 decade counters. Now, every time we count to 16, we want the chip select line to go up, and then the count to be reset, and then restarted all over again. So we're going to do that using a D flip-flop and a delay signal with an op-amp and a resistor capacitor network. And so I have the red wire going from the 1, or the tens digit, which is a 1, over to the data signal of a D flip-flop, and the blue wire from the counter is going into the clock signal of the D flip-flop, and this basically sets the D flip-flop to high every 16 counts. Now, in order to make it go low again, I want it to go low very quickly right after it goes high, so I have from the Q output of the D flip-flop, I have a 1K resistor going to the reset bit with a capacitor going to ground, so that it provides a slight delayed signal, and this is a 27 nanofarad capacitor, and that delayed signal, so after that slight delay, it will reset the D flip-flop to low. The output of that Q, one of which goes to reset the counter, the other of which, since it, after a low-pass filter like this resistor-capacitor combination, goes to a op-amp comparator, and that op-amp comparator provides, you can adjust the reference voltage. In this case, I have the reference voltage adjusted to about 3.5 volts, and at 3.5 volts, it provides this very short signal, and that white wire coming out of it is the resulting signal. And when I did that, it provided a wave, or it provided a short pulse that's it was almost 5 volts, because the op-amp can't go all the way to the power rail, the 5-volt power rail. I have it between 5 and 0 and ground, and that allows that chip select signal to go high right after. And so the resulting waveform is this, where you have the chip select peak going high every 16 bits, or every 16 clock pulses, and right in the middle of it. And when you attach those to the respective portions of the AS5047, what you get is a nice SPI interface. And so if I was going to put this wire, which is on the data line, showing the data coming out of here's the data coming through. And it's SPI, and it's 14 bits of data. And if I'm going to test it out with the magnet here, you can see that the data patterns change according to the position of the magnet. Here's a very high bit value. There's a very high bit value. You can see after the yellow pulses, there's a long high peak. And if I turn it clockwise, it'll go to low value. There. Right there. That's the 360 degree to 0 degree transition. And it's pretty rock stable. So that's a much easier interface to build than the I2C one. When you use SPI, it's only a handful of chips, a clock, some counters, an op amp, and a D flip-flop. So all in all, I could probably fit all that into one board and make a nice little hardware-only serial peripheral interface. So here's the SPI interface, and that's the whole module that does it. This is the SPI device, the AS5047P, and literally that's it. And when you put the magnet on it, it registers. Data is pretty consistent. And if I stop it for a second, you could see first bit is always the parity bit. Second bit is the error flag, which is low, which is good. Here you get 0 parity and 0 error, 0 parity. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's an odd parity, so that works. If the parity is right, the error flag does not come up. And yeah, that's on. It's working just fine. Now we have to find a way to display and interpret the data. And as you can see, here's a very low value here between the two chip select pins, corresponding to 0.46 degrees. Here's a very high value of data. And you can see this is equivalent to 359.89 degrees, and the digital value corresponding to it down below. Here's what the data looks like. You get a parity bit first, and then a parity error flag. So if there's an error, you'll see that flag go high. And parity is calculated by the device itself. So parity just means the number of total ones. If it's odd, you get an odd parity, which is a 1. And if it's even, you get an even parity, which is a 0. And the total number of ones in the data, including the parity bit, have to equal the parity. Otherwise, there's an error. So now I built this little wheel using a coaster, and I fit the magnet on it. And so the device is inside, and it's a pretty smooth run in order to find the angle. And as you can see, the angle going up and down based on where the wheel turns out. Here's the 0 crossing point, and you can see between, if you go there, that's the point where it goes between 0 degrees and 359.89 X degrees. And it's working, and you can see there the parity bit is flashing on and off, and then the error flag is the second bit sent, and then it sends the most significant bit first and the least significant bit last. And here it is at the 0 position as the lowest possible point. So I think that this interface is a good one, and it's working and it's stable. So we're going to make the display for it now. And to make the display for this, we're going to use the same display that I used before, which is just using a shift register to shift the serial data in. I'm going to use the serial clock as a clock for the shift register, and I'm going to use the chip select line as the latch signal. And so this will drive the data through the 16 bits, which means 2 chips worth of 74HC595 serial in, parallel out shift registers. Here it is, SPI, matching the data that we see there. This is the parity bit. This is the error flag, which is off, which is good, thankfully. And as I rotate this, goes low. Here's the crossover point. So high, let's go down. That's a really low angle. It's at the hysteresis point. See where that is? It's barely. Barely a degree, not even a degree. Look at that, 1011, but it fluctuates between the hysteresis point. And that's how much easier it is to display data with SPI from a magnetic rotary sensor. "14 bits of data. Here's the final product. An SPI interface for an AS5047, which is in this, underneath this board. Magnetic rotary encoder, absolute angle position sensor. It's got 14 binary bits of data that it provides. This second to last bit, which is off, is the error bit, and this is the parity bit, which I don't necessarily need to display either of those two. There's a nice low angle. It gets lower. Now here's the point where it crosses from 0 to 360. the oscilloscope anymore. We finally have an output displayed on 14 bits of data here. And it's reading around 375 hertz. Pretty good frame rate. Updates the data very quickly. And as always, I'm going to leave you guys with the schematic for the interface. And this is a great board, and SPI is way easier to interface hardware only without a microcontroller. So thanks for watching. I learned something. I hope you did too.